dinner, but we're going to get started. So before I talk, I will warn anyone who's really good at computer architecture knows a lot about system debugging. This will not help you in the slightest, okay? This is a very brief introduction. It's specifically for Brimstone. He requested it. So we're going to focus a lot on computer architecture styles, very specific parts of it related to debugging. We're not really going to delve into specifics of a system. Every debugger is different. Every system is different. If you work on a different CPU, it's a different way of doing it. So if I stand up here and tell you dbg and then type x/x to do a dump, that's not going to help you on Windows. Okay? So we're not going to cover that. We're going to cover the theory behind it. I just want to pre-warn everybody on that. Other than that, my name is Tyler Pitchford, a.k.a. Trip. You may have known me from the co-founder of Azurus, the BitTorrent client. I'm now an appellate attorney in Florida. I'm also the CTO of a software company in Nashville. That's why I'm here. So that's what I do. That's my background, and that's what I'm here. If you were at DEF CON, ShmooCon, or any of the other cons last year, you probably saw a talk on, or you may have seen a talk on the Fourth and Fifth Amendment. If so, that was me in a suit. You will see I'm now wearing my computer suit. Actually, you probably saw me this at the rest of the con, except for when I was talking. And usually I take these off, so you can't tell who I am. But it's fun. So let's get started. This is an introduction to reverse engineering. If you're looking for something else, you should probably leave now. Moving on. All right, fine. All right, so you break it, you bought it, or whatever. Reverse that. Thanks. Do something. Okay, so an overview. We're going to cover an introduction to reverse engineering. We're going to cover the process of reverse engineering, an introduction to computers and software, reverse engineering and software, specifically the tools, one example, and you'll understand why one is all you need. And then question and answers if I feel like talking to you. No, that's not true. What is reverse engineering? So it's the process of analyzing a system to identify its components and their interrelationships to create a new representation of that system. So anybody ever reverse engineered anything? Doesn't have to be software. It can be anything. Anything? What? All right. No, I always like to picture that the original reverse engineering was two cavemen, and one guy was like, that's a sweet axe, and the other guy beat the crap out of him and then took it apart and made his own. But I can't substantiate that, but I think it's true. I'll put it on Wikipedia later, and then it's fact, right? But so this is basically it. You build something's been built up, and you take it apart. All right. So it's building versus breaking, as I always refer to it. An engineer builds something. A reverse engineer usually takes it apart. We pull it apart into its core pieces. So engineering is designing a product, constructing a product, etc. Reverse engineering is deconstructing, investigating the design process, and a lot more. It's really like taking a puzzle and building it. It's a lot of fun, especially if anybody likes lockpicking, if they like computers at all. It takes a lot of time, but it's really awesome. The difference is you have to practice it. It's not something you can just pick up and go with. You work at it. You work hard. And it takes a lot of research. It's a lot of devotion. So it's more than just code. You can reverse engineer everything. Medicines. Has anyone seen the reports on South in Africa and India where they're reverse engineering and put out medicines that companies wouldn't put out? Now, a lot of that's done from the patent process, but at the same time, sometimes they do research in how the process was done to try to get back the trade secrets on it. So it's actually saving lives. You've got food flavors, they reverse engineer, actual natural ones and artificial ones, like the fake banana flavor. They want to make it taste like banana, and they got to deconstruct the chemical parts. Materials, architecture, physical products, Mother Nature, languages. The Rosetta Stone, classic example. They pulled apart languages into semantics and built it back up. And we'll talk a little about that, but we're gonna move specifically into software eventually. So what's the use of reverse engineering? There's fun and profit. It's just fun. I mean, a lot of people do it as a pastime. You can actually save and destroy lives, save and destroy companies. If you don't like somebody, if you reverse engineer their product and it's covered by a trade secret, they're SOL. There's no protection on intellectual property when it's a trade secret, as long as it's divulged legally. Once it's in the public, it's gone. We can talk all about that legally if you want to afterwards. But so like Coke, for example, Coke is Mountain Dew, but a Coke, if somebody reverse engineered the Coke formula, which they've been trying for years, if they actually successfully reverse engineered the process, Coke couldn't do anything. Someone could market another product, call it not Coke, and you're good to go. Freedom, software. Everybody here uses software? Everyone? Anybody? Anybody doesn't, you're probably in the wrong spot, seriously. But software, a lot of times, there's a sweet piece of software and they won't release the source code, but you want it. You want to know how it works. Maybe it's doing a sweet hash calculation or something. You want to know how that works or how it's doing its protection on the system. So what do? You've got the source code technically in the binary format, and as long as there's not a contract in the way, you can pull it apart and release it. It's clean room style. You guys have all heard of the clean rooms? All those different projects, Wine, for example, they do it in a clean room. They reverse engineer the binaries without any help from Microsoft or any documentation, entertainment materials, and when they release it, it's free. And why the hell not? It's fun. So it's a way of thinking. Reverse engineering. It's really a way of getting your mind around something. You have to investigate the problem. You really become I won't say immersed, but you have to focus on it. You have to think about it. You've got to come at it, and I hate the phrase "think outside the box" because you're not thinking outside the box in this. You're thinking, just forget about the box. Just go at it. You're going to look for clues and hints. It's really a process of finding stuff. So reverse engineering requires research, analysis, a lot of patience. I will promise you that. A lot of caffeine. Always have one of these or something else handy. You got to have the hacker mentality, the hacker spirit. You got to want to take it apart. If it's a job, that's okay. But where's N80? He reverses for a living, doesn't he? Yeah, he does it for development. He does it for a living. It's fun when you're doing it for work, but it's not fun. You want to be doing something for yourself. So go at it and have a good time with it. And don't constrain yourself to software. Take apart anything. Look at it. Pull it apart. If you want to make your own clock, pull apart the clock and see how they did it. It's cool. So there's 1,000 ways to skin a carrot. And what that means, like I said, I was a vegan, so we couldn't put cat because people will bitch at me. So we use carrot. But anyway, what I'm talking about here is if anyone's ever built software, anyone a software engineer? Actually build software for a living? What's everybody else do? They're all unemployed? Cool. Everyone fun employed at least? Everybody having a good time? Like, woo! No. No, but there's a bajillion ways to build a piece of software. You can use a for loop, you can use a while loop, you can use a goto. Don't do that if you don't have to. Just saying. You can do OO style, you can do functional, you can do all these different ways. You can use different programming languages, et cetera, et cetera. So every time you reverse engineer something, it's going to be different. And there's going to be someone did it a different way. And you've got to be conscious of that. And there's also 1,000 ways to get inside the product to figure out what it's doing. If you're debugging a piece of hardware, you might have to decap it, which is to pull the electronics, essentially pull the top off the hardware and see what's inside. It's a different world. You have to dissolve it in hydrochloric acid or something. What is it? I forget what they use. I think it's hydrochloric. But if you ever want to know about that, talk to Travis Goodspeed. He gives great talks on that. But there's an infinite number of ways to build something. That means there's a different, conversely, there's an infinite number of ways to take it apart. But not all ways are equal. I can try to reverse engineer a piece of software by reading the zeros and ones. That's going to suck. You might look really, really cool for some computer chick, but other than that, you're just going to waste a lot of time. You will look like Richard Stallman by the time you shave again. It's not something you want to do, So we use tools. We have tools for this, and we have tools for different types of reverse engineering. If you're going to do biochemical reverse engineering, you're going to have a lab. You're going to have microscopes. You're going to have chemicals. If you're going to do software engineering, we're going to have some tools, and we're going to talk about those. But on that point, Occam's razor. Everybody's heard of it. Everybody's seen Contact or Reddit, hopefully. Everybody talks about this, but it's true. This is the Latin. If you reverse engineer or translate into English, you end up entities must not be multiplied beyond necessity. Or if you move it up again to like plain English, when you have two competing theories, the same solution, the simpler one is better. And when you're reverse engineering, a lot of times you'll be looking at a problem. You'll be stuck on something. You'll be thinking, how did they do this? How's this happening? And a lot of times before you actually get into the opcodes or the hex of a program, the binary, you're going to want to figure out and map out how it works. You want to make theories on what it's doing. So these are like your key points, and we'll talk about that. But you want to make sure that you always check the simplest solution first. A lot of times that's true. But a lot of times in reverse engineering, and conversely, you've got to know your enemy. Anybody read Sun Tzu? You got to realize who you're fighting against. And if it's a product that's been reverse engineered a lot, they're going to put defenses in. And it may be really, really obfuscated. We're actually not going to talk about anti-debugging techniques. If anyone wants to talk to me afterwards, we can. It's part of the fun to figure those out. But the truth is sometimes they will throw in kinks and quirks, and they might write ridiculous code specifically to throw you off. Okay? Or you guys have all seen. Anybody ever modded a piece of hardware, like a game console or something? And you put a mod chip in, and they've got epoxy over top the chips. That's stop. It's a debugging. It's a reverse engineering slowdown. You can get it off there. It's not always fun though. But just always keep in mind, if you're stuck on something, try the simplest thing first and then move out, okay? So if you can rule out something, good. If you can't, keep trying. And this one I always just love, Howland's razor. This is great. Anybody have a corporate job? This is the most useful thing in the world. Anybody have managers? Oh, yeah, man. Because never attribute to malice that which can be adequately explained by stupidity. Every day this keeps me calm. Every day. I swear to God. I'm just like, why would you do? Oh, never mind. It's cool. Whoa. No, I swear, this is probably the most important thing in this entire talk. I'm not even kidding. Memorize this. Write it down. Tattoo it on your face. It is brilliant. Oh, you can't see it? No, well, yeah, you got to have a mirror, though. You put it on your arm, whatever you got to do. This is just, if I could put this on my wall without getting yelled at, I would. Except my boss would walk in and I'd be like, look, and then I'd get in trouble. So we just ignore that. But, wait, what? Oh yeah, Brett. We don't talk about that at all. So let's get into computers now. All right. Everybody knows the Steve Ballmer. Microsoft has developers. Reverse engineers have memory. Literally, this is your key. This is what, in my opinion, you can all argue about it any way you want. A computer is memory. That is all it is. This is everything that it is. It's memory and conventions on top of memory. If you understand how memory works, you can take apart anything. You can put it back together, and you understand how a computer works, okay? All the hardware and whatever is just manipulating memory. So the parts of computer. Anybody know the parts of computer? Everybody? Does anybody not know the parts of computer? That's above high school? Anyone? Awesome. Okay, so we've got, for our purposes, it's all memory. We're talking about registers on the CPU. Can someone tell me what a register on a CPU is? What? It is. It's a special piece of memory in hardware, essentially. Okay, let's just call it that, and we'll leave it there. And RAM is? You guys are good. Who's been paying attention? No, yeah, exactly. It's memory. It's good. That's what we're going to be dealing with. So anything on your hard disk is on what? Okay, and when it's transferred to RAM, and when it goes into the register and the CPU executes it? All right, you guys are good. So what are we dealing with? All right, not Pez. It's so good. So, let's just curse. What the fuck is 42? Well, it can be, exactly. We only remember it because of memory. No, this quote, somebody, please, where's it from? Excellent. If you don't know that quote, go read the damn book. We got Arthur over here. It's a great book. By the first 3 pages, I think I had tears coming down my face, specifically because of the digital watches. Hilarious. I mean, the guy didn't know it had to get nailed to a cross. Fucking hilarious. Brilliant stuff. But besides the meaning of life, what the fuck is 42? And this is kind of the meat here. So pay attention to this. This is important. A lot of people don't get taught this in computer science anymore, and it drives me insane. They don't teach people this in programming for some reason. I have no idea. But let's see what happens to 42 in different forms, okay? This is 42 in binary. So everybody knows a computer runs on zeros and ones, binary, unless it's a trinary computer, and there's like 6 people that have those, and they're really weird professor guys. If you have one, cool. Weird. But most everybody, anybody have a Mac? Wow. There's like few cool people. How about Windows, anybody? Well, one guy will admit it, 2, 3, 4. Oh no, there's a lot of PCs here. And then who's got Linux? Yay! Linux is the only one that runs on binary. That's true. It's on Wikipedia. All the other ones are weird now. All the modern CPUs execute on binary. They deal with zeros and ones. And why is that? Anybody know? What's a CPU made out of? I heard transistors. And what states do a transistor have?
On and off.
Yeah, which is also known as?
Ones and zeros.
There we go. This is how computers work, people. So this is what 42 decimal looks like in binary, or base 2. Okay? This is what 42 looks like in octal. It's 52. Now octal is base?
8.
Okay. Can somebody else name another base? 16, base 10. So 42 and base 10 is going to be what? 42. All right. What's 42 in hex? Anybody know? Anybody know their ASCII charts? Bait? No, beat. Well, you're correct if it was hex, but if this is decimal, then it's going to be the opposite actually on the chart. But it's going to be 2A. Okay, 0x2A is the right way to represent hex in C at least. But he is correct. A capital B in ASCII is 42 hex, or 2A det. We won't talk about it. But so in ASCII, 42 is actually the star. And what's ASCII? Does anyone know? Thank you. American Standard Code for Information Interchange, a.k.a. a what? A format, a protocol, a specification. This is an agreement between computers that 42 decimal is this symbol. Okay? Does that make sense to everybody? This is I've gone over to Presmike and I said 42 will now be star whenever I decide it's ASCII displayed. Okay? And that's all it is. Without these conventions, there's nothing. There is nothing between computers. And that's why executables on a Mac machine won't run on a Windows machine. They use different standards. Now, most of them agree on ASCII. They'll all pull out ASCII. Anybody know another character standard? EBCDIC, Unicode, UTF-8, UTF-16. Now we have UTF-32. There's tons of these. There's Windows ISO. Anybody opened up a Word document and it was all crazy looking? And it was like character format can't be found? That's exactly what was happening. It was trying to process this memory, and what'd you get? A bunch of crap because it didn't know what the hell it was. So let's see. This is an interesting one. So 42 and x86 opcode. Does anyone know what an operation code is, an opcode? So a CPU runs on a series of opcodes. You give it a byte, or several bytes, depending on how large the opcode is. Now we have 32-bit opcodes, whatever. And it decides to do some action on what? On memory, exactly right. So memory is affecting the memory. So on an x86 opcode, 42 in decimal, which is 2A in hex, ends out being a subtraction command. It's actually subtract, I think it's GB from EB, but we won't talk about those right now. If you guys want to learn assembly, you can do that on your own. We will talk a little bit about it, though. So what do we have here? We end up with a big C of bits. Some people say a string of bits or a stream of bits. I think of it as C because you can jump around in this if you want to. It's random access, right? I can go from point A to point 1000. I can go back to point 2, whatever. I can move around. I don't have to go 1, 2, 3, 4, 5, 6. A lot of people like to display memory as just a line, and that's okay. It's great for a display, but it's not true. It's not really how things are. So without these conventions, without ASCII, without these agreements on how strings and stuff work, or just these opcodes. For example, if I put 2A into a binary, if I'm running not on an x86 machine, but I'm running on a PowerPC, it's not going to do subtract. I can almost guarantee it's not going to. I don't know what it actually does, but it's not that. And that's a problem. That's completely a problem. There's no way for it to communicate. So when you're reverse engineering something, what do you have to know? You have to know the standards. You have to know what you're working on, how it was engineered, how it was built, what its foundation is. And that's what you're going to have to learn. That's not what I'm going to teach you. I'm going to teach you the theories behind it. But the specifics of your machine, if you're hacking an Arduino, is it an ARM chip now? It's Atmel. It's Atmel, isn't it? Yeah. So you're going to have to learn the Atmel opcodes to understand it, to take it apart. If you're going to use an ARM chip, you've got to learn ARM. If you've got to learn PowerPC, et cetera, et cetera. So these zeros and ones make no sense without the proper foundation, without the proper tools. Now, almost every machine has a debugger. If it doesn't, you probably don't want to be reverse engineering. It's not going to be fun. But so until they actually have these outside meanings, they're nothing. There's nothing there. It's just a bunch of zeros and ones. Okay? So let's look at strings. Does anyone who programs, you guys have used strings before? Anybody written anything bigger than, well, shit, if you use Hello World, you've done this. Anybody written Hello World? Not even a programmer, just did it? You guys are awesome because you can now you can follow along. Did anybody use C to do it? Anybody? All right, cool. We'll actually make some sense of this now. So how do we get from 0010 space 1010 00000000 in Big Indian, we'll talk about that in a minute, to star? And quotes in programming, double quotes are usually representative of a string. So how do you get to the string star from that? So without this convention, there's what's known as a C-string convention. It's the convention in C for how strings work. And that's the convention here, specifically the string convention, is null terminated. It means a series, a byte at the end, 0 bits, or 8 bits, excuse me, aka 8 zeros, is a null terminator. It means that's the end of a string. Anybody know what happens if you don't put that there and you keep running through memory? Potentially, if you keep copying into a buffer that's not big enough? Buffer overflows. You guys are all now hackers. Awesome. No, it's exactly what happens. So someone broke the convention. Somebody said, I'm going to copy a string, and it's going to be 0 terminated before this certain length. And if they didn't do a check on it, and they just copied the memory over top of what? Other memory, and now has corrupted them what? And the computer does what? It screams, oh shit, and does whatever the hell you tell it. It's awesome. I've actually seen it. The Intels are the loudest. No, but it's, so this becomes 00101010 becomes the ASCII character star, okay? This 00000 becomes /0, or aka null terminated in a C binary. So languages which understand null terminated strings see this star quote. But in memory, it's all a bunch of zeros. If you look at this at a binary dump or a hex dump, it's going to look a little different than this. It's going to look 2A and then 0, 0, okay? 0x, 2A, 0, 0. But depending on the Indianness, and we'll talk about that. And languages understand it. So does everybody get the convention? Everyone? I'm going to move on. All right, good. So linked prefixed. So how would that work? What would that look like in memory? Can anyone tell me? Well, it would look like memory. That's right. What would a linked prefix look like? You don't have to give me the binary. You can give me the hex. Or you can just tell me in decimal if you want. Say it in English. Okay. Okay. Yep. No, exactly. You'd put the number of bytes in front and a length, and you'd have some format. It might be an integer. It might be a long, which is 64 bits or 32 bits on standards. We'll just use those. And then the system would read that length and then read that many bytes along. Okay. Does that make sense? The Xbox is actually hacked because of a flaw in that. Their specification, they didn't check for buffer underruns or buffer a negative value in the integer. So what happened was they loaded too much memory from the linked prefix on the file name. So it was the font file. The format was that. It probably doesn't make much sense, but it's cool. It's useful. Linked prefix. So it's just different. So in memory, it's just going to be represented differently. But sorry, I had to include this. It's funny. One little, two little, three little Indians. Has anyone ever worked with Indianists? Yeah, it's annoying as hell. Has anyone have problems converting from little to big or middle? Yeah, it's terrible. Middle's the worst. Anyone actually use middle? I have. It's horrible. It's a horrible world. But the zeros and one is different from machine to machine. Completely different. So even if you're looking at the zeros and ones and you're like, all right, I know what's going on here and I've got the format, it's different from an x86 chip to a PowerPC. The format that it's actually in. If you're looking at Java code's actually in Big Indian. But Intel chips are in Little Indian. So if you're doing mixes between C and Java, it gets all ridiculous. Networking code is in Big Indian. So the bytes come in, and we'll explain how those look in a second. Just follow with me here. So the bytes come in a certain format, and they say, on the other side says, well, I read in something, and it's, what's the C command? BTOI, something. It's a command to read a byte off of network order. I think it's byte network order to integer, something like that. But it reads off this format, and these come in, okay? And the Middle Indian is ridiculous. It's crazy. It's not used very often, thank goodness, but a lot of people in formats for some reason use it. I have no idea. So Big Indian, if this was a lower memory range and that's a higher memory range, so 0 to FFFFFFF, which is the highest value in hex, you're going to get, if I had this in memory, it's going to be 0. These are bytes, single bytes, so the atomic scale is the lowest amount of memory that a CPU can read. So on most machines, it's a byte. That's the smallest you can get. You can't read a bit. You can read a byte, okay? You're going to get A, B, C, D in Big Indian. That's the order. It goes from the lowest to the highest. Little Indian goes in reverse. It goes D, C, B, A. So on an Intel machine, this is what it would look like. And when you're reverse engineering a piece of software, this is really important because you're looking at a hex dump, okay? And this hex dump is going to have a hex value in it. And if it's more than 1 byte, if it's 2, if you're looking on a PowerPC machine, if you're looking for the characters A, B, okay? And that's like specifically what you need to find. In a PowerPC machine, it's going to go A and then B. But on a Intel machine, you're going to have to be looking for the reverse, B and A. But almost every debugger displays it in regular Big Indian format. So you're going to be looking for different stuff, if that makes sense. All right. You'll get there if you do this. And Middle Indian is just ridiculous. You see how it's interleaved? B, A, D, C. Why did they cut it in half and then switch them? It's really weird. If somebody tells you to do this, tell them to go to hell. You can tell them I said it. It's fine. It's cool. It's totally cool. They can call me. I'll do it. The instruction set of each CPU is different. We talked about this, right? So Intel is different from PowerPC. It's different from ARM. It's different from PIC, okay? So if you're reverse engineering, you've got to know the basics of it, right? So, of course, binaries don't agree. So the binary format, an executable format in Windows is the PE format. On OS X, it's the Mach format. On Linux, it's the ELF format. Now on OS X, you've got the Mach universal format, so there's actually 2 binaries in one. And there's theories that there might be a third one inside there. So you have 64-bit, 32-bit, actually 4. PowerPC 32, no, they won't include PowerPC 32. It'll just be Intel 64, Intel 32, and PowerPC 32. So your binaries are actually 3 times the size they should be. It's pretty sweet. No, not at all. There's a cleaning program, actually. You can actually scoop out all the code that you don't have, which you think would be intelligent. You think when it would install, it could do that. I should call Steve Jobs. But yeah, good. And then there's packed, a packed binary format. Does anybody know what that means? Can anybody tell me? It's obfuscated, scrambled. It's somebody compressed. Usually it's a compression on top of it. So when you try to load this into a disassembler, it's not going to make any sense because there's a small piece at the beginning, the header, just the opener, the preamble, let's say, that de-scrambles the code. And this is actually how viruses used to transmit. They used to call them, what was it? Meta whatever. Whatever. Viruses used to do this to get around detection because what did the old virus scanning stuff used to just do a signature? And if you changed the values, the signature came out wrong and they didn't match. So if you just kept changing the code in this packed binary, nobody would know what it is. And to get a packed binary, they call it dumping. You unpack it and dump it. And that's a pretty advanced technique. But the theory is you've got to have the information in there. So when it unpacks it, it's in memory somewhere, right? So if you can find it in memory, you can dump it out, and then it's a clean executable. Because the computer's not going to execute this, right? This packed binary doesn't make any sense to that CPU. None at all. So it has to be descrambled before the CPU can execute it because there's those protocols, those specifications. So you know it's in there somewhere. A side note, disassemblers. If you're working in a disassembler, if you learn certain ones, like Ollie debug is Intel format. GDB is AT and T. And it's a format just on how the assembler outputs code with % signs and whether the opcodes are reversed or not. So if you learn Linux debugging, for example, on Intel, you're going to have just an annoying time because you have to learn the other syntax. It's easy to convert, but there's some quirks in it. Just be aware of it. So what about reverse engineering software? Let's get to it. Okay. What's the process? It's pretty simple. The typical development process of building up a source code, engineering a piece of source code, is you write the source code, you compile it or assemble it if you wrote an assembly, and then you come up with a binary, right? And you ship that binary out to people or clients or whatever. The reverse engineering process, you get the binary, you can decompile it if possible. VB, 5, 4? One of them before they had the VBPE code would let you just disassemble it. I mean, the code would pretty much come out perfectly. Java and .NET, almost exactly word for word when you decompile it. It's not disassembly, it's decompilation. And a technique to get around that's called obfuscation, but it's not that tough to get around anyway. And then there's if you can't decompile it, you disassemble it. So you dump it down to this series of opcodes. And at that point, you've actually got the source code. And sometimes if it's open source, has anyone actually reverse engineered a piece of open source software? Pulled out the source code? I have. There's some nasty code out there. It's terrible. I think they do it on purpose just to mess with you. But you pull it apart and you look at it. A lot of Apache projects are like that, but it's all right. So you've got this disassembly. So if I'm shipped a binary, what do I have? Well, I've got memory and I've got an executable. I've got zeros and ones, but I've got what? What's in there? There's assembly, right? There's these opcodes in there. And if I dump the assembly, if someone had just written that code by assembler and hand compiled it, or hand assembled it, I should say, you would have that same binary. So you've got the source code. It's just really, really a pain in the butt to read usually, if that makes sense. It's not clean. It's not, if this, if that. It's a bunch of jump statements, no ops, whatever, a bunch of hex codes. But you have the source. You always have the source. It's there. That's not always true. Can someone give me an example when it's not? Something you can't reverse engineer without going outside your machine. You play World of Warcraft. You have to authenticate with the server to figure out what's going on. And actually, one of the odd ones, there was a piece of software back in the day. Anybody remember WarFTP? WarFTPD. It was an FTP server for Windows. And when the crackers actually went out, I knew one of the guys who programmed it. It was funny when the crackers went in and reversed the serial generator for it. The code in the actual binary didn't include the entire serial generation. It included a validation routine that would pass certain serials that were bad. And when the program executed, if the serial was incorrect, when it used that serial, it used that serial for certain jump tables. When it used that serial, if it didn't actually match the serial generation that was actually from the company, the machine would crash. There was a null pointer exception. It would fall out. The memory was bad. It was corrupted. So it was funny because the serial generation, the validation routine, was actually less complex than a generation routine. You didn't have the source code for that. It didn't exist. So you'd have to actually go in and figure out the op tables, what was happening, and go in and fix it. I don't know if they ever did or not. It was pretty funny, though. The guy who wrote WarFTP thought it was hilarious. He was like, oh, I didn't even mean to. But it was entertaining. So when you're reverse engineering something, you have to find the clues. You have to find the clues to solve the puzzle. And there's lots of ways to get these clues. There's lots of ways to figure out what a piece of software is doing, and there's lots of hints. And you'll be surprised at how simple it is to reverse engineer stuff sometimes. We're going to work through a simple, very, very simple serial generation. It's not even a serial generation per se. It's just a root password. And oddly, this is extremely indicative of what most reverse engineering software is. You'll be quite surprised. I think it's like 8 or 10 lines of code, but 99.9% of the time, if you're going through a piece of software looking for something that's doing a validation check, this is what's going to show up. So you always have the source. Well, cover that. Okay, this is something I teach all my students. I used to teach a lot of programming classes, and it was taught to me actually by my father. But source code is just like reading a book. It's one line from top to bottom, left to right. Okay, one line at a time, top to bottom, left to right. And that's the same in assembler. Now, we're not going to talk about multiple core systems. We're not going to talk about superscaling and pipelining. Okay, those technically all execute one at a time. It's just multiple things are executing one at a time. But if you're looking at a piece of assembler, if you're looking at a piece of source in a debug, it's going to go 1, 2, 3, and if it's a jump command, it'll jump somewhere else. But it still did what it said, that one line, and now it's next to the next one. Does that make sense? It's very important, because some people look at code and they get really confused. They're like, what's all this crap? There's all this crap on my screen. I don't know what the hell I'm looking at. If you just look at it real methodically and you write next to it what's going on, you can get through it. You'll be amazed. I've actually had programming students where I had to sit them down and was like, write a comment next to every line on what it's doing. And it works. It takes a while, but once you get used to it, you'll start understanding that software is really very, very predictable. There are no magic gnomes. I know it breaks someone's heart. I know. But there are no magic gnomes in your PC, sadly, unless you put them there. But system architecture dependent. So see above. Remember we talked about how everything's different, blah, blah, blah. If you decompile, these are the tools, right? You got to have your right set of tools. You don't go fix a car with a Play-Doh. I mean, you might. It'd be funny. But You've got a decompiler. You've got a disassembler. So on Linux, you've got object dump. On Mac OS X, you've got OTool. On Windows, you've got WinDAS, and there's other different tools on Windows. Debuggers, GDB is a classic on Linux. Some people hate it, some people love it. I think it's great. Ollie debug on Windows is really nice. It's a mode kernel. It's a user mode debugger, I should say, not kernel mode. So if you're trying to debug a device driver, it's going to be a pain in the ass. Use, WinDebug? Yeah, and you'll have to have a second terminal machine. If you're ever working in the kernel or a driver, you're going to need a second machine. Okay, don't try it in a VM. It's just bad. Bad mojo. And then Soft Ice. Anyone ever use Soft Ice? It was awesome. Like, anyone had a job back in the day, it was really, really great software. And then one of the greatest things, resource monitors. So a piece of software is going to be touching parts of the system, right? Finding these other pieces of memory. You're going to be looking on the hard disk. It's going to be looking through memory. It's going to be, accessing different peripherals. The registry in Windows example. And you can monitor those. If you monitor what's going on, you're getting a better picture of what's happening. So if you know how it was working, you can figure out how to make it work the same way for your software. So an example. We're just going to cover one. I know it sounds kind of weird, but you'll see why. So this is our program. All right, really simple. Enter your password. I typed 100, I got wrong back. I enter my password, 200, wrong. Enter my password, 50, wrong. Enter my password, 42, correct. What do we learn from that? What do you see here?
Taking input.
Okay, it's taking input. What else is it giving?
Output.
Output. What's it telling me? When I put in the wrong password, what am I getting?
Checking the input to see if it's good or bad.
Okay, and I'm getting a visual confirmation here, right? So when I type something in, it says wrong. I know I can look for that, right? Somewhere in the code, there's going to be this wrong. Somewhere, right? So I know if my password has failed, I'm going to get this prompt back. There's a visual confirmation. There's some external output this program is giving me, and that's a hint of what's going on inside. And at the same time, I had to enter something. So to read it in, it's got to have some kind of a read command, right? There's got to be something it's doing to look for it. So right there, you've gained a lot of knowledge about what's going on right here. It's reading memory, and it's writing memory to the output, right? Okay. And actually, if you run this and you type in a different, like anything that's not an integer, it'll actually cause a big bug, and it just loops forever, and it's really funny. But that will actually give you input that it's only taking an integer as the source, but that doesn't matter. So what do you see? We covered that. This is the source code. This is it. This is the entire source. I will give you the source code, and you can see it, and we will decompile this later. We will figure out what's going on in here. So you've got your includes. Everybody used C before a little bit. Do I need to go through it a lot? No? Good. Okay, so int main is just the entry point for the program. Define password 0x2a, so that's our password. Nice and easy. Bool finished equals false. Input. Scan. So this is printf, right? This is our write. Remember that write? Enter your password. There's the first output. Scanf. %d just means read an integer. This has reference to input, so write it into int. Input equals password. If not, finished equals true, so it'll exit. Else, it's going to print out wrong. And if you get out of the program, if the while loop exits, it's going to print correct, and the program's going to exit. Okay, does that make sense? So this is source code. This is C source. What am I going to do when I get this compiled? What's going to happen? Yeah, it's going to, well, some compilers used to convert to assembler first. It would assemble it, and then it would assemble it to a binary. Most compilers go straight to binary now. You can actually output C code to assembler with GCC if you use the -S switch, capital S. So if you ever want to play with code and, like, if you see a strange piece of code and you're not sure what's going on but you have a clue, write a little sample program, compile it with -S, and you can look at the assembler. Okay? So this is what this was compiled with: GCC -wall M32, because I'm on a 64-bit machine, so I needed a force 32-bit. Otherwise, the registers will look all crazy and start with an R. Password.c-o, output a binary named password. So this is the binary. There's actually a lot of white space in here that I dumped out. It's a null terminated to space out the sections, but we're not going to talk about that. This is, if you open this in a text editor, this is what you get. Can anyone read that? There's parts you can read, but can anyone actually understand that? I know one guy who can. He's crazy. He's awesome, though. He was a Microsoft kernel developer. So they actually have good people. I don't know what they do to them, though. But see, this is your text section, and you got your data section, and we got your code section down here, and you'll see some includes and whatever. And this doesn't make much sense, right? Somewhere in here, there's a protocol that's saying this is what this binary does. This is what this means, and we're gonna look more at what that is. So if we disassemble it with OTool, OTool is a disassembler for OXX. It's the object, whatever they call it. You can disassemble object of C code in this, which is the OSX native code. But you can take apart native C too, okay? And this is what you get. This is the disassembled code. So right here we have the memory address, the offset, and these are the actual hex. These are the opcodes, okay? This is actually the raw data. This is what all that crap was in hex, just the hex printouts, okay? And over here is the assembler. So these are your commands that are being executed, and they're pretty easy. Assembler, the one great thing about assembler is it's usually named pretty aptly. So push is going to push data onto the stack. Move is going to move data. Subtract is going to subtract. And is going to do an and operation. LEA means load effective address. It's basically a point of reference, okay? And if you look these up, they're all like shift left, SHL. It all makes sense. And the L's at the end are because this is a 32-bit machine and this is the AT&T output, so ignore that. But what this is it all makes sense, okay? And if you pull up a similar reference, you can literally sit down next to this and write down exactly what it's doing. You can figure out where the registers are going and what's happening. It's all right here. You just have to take the time to do it. Most people freak out and are like, I know what this says, and run away. There's no reason to do that. Just sit down, write it down one at a time. A lot of this is preamble code, so a lot of this is just setting up the stack frame, setting up all that stuff. And you can, once you get used to it, you can skip all that. You can find exactly what you're looking for, especially if you've paid attention to how the program is working. Okay, those visual stimuli and those outputs, those external events that you were seeing, are giving you hints. So this call main is going to execute the main function. Okay, there's only one function in this program. It's main. So this is what the main looks like. Okay, it looks like a bunch of crap. Somebody here can read this, right? I know you can. Come on. Okay, this is a bunch of crap, right? But what do you see on the side? Anybody see those? Anyone? No? Anyone awake still? Cool. No, puts and scan. What do you think puts does? Put stuff on the screen. What do you think scanf does? Call scanf. And anybody use printf? Printf prints stuff to the screen. Scanf would read it. And if I didn't know what that was, where could I go? Google. Exactly right. We'll actually show you the output from that. And does anyone remember that star in ASCII? See that? All right. Nice visual stimuli, all right? But so if you use Google, you can figure out what everything does, right? I see this weird word. What the hell does it mean? Puts. Include stioh, which means the header that I included at the top. The function puts writes string to the stout, puts returns a non-negative or successful end of failure. Here's the prototype of the method. So it takes one parameter, right? This pointer to a character array or a string, okay? And scanf. Scanf, it reads input from the standard in, okay? And it takes one character format and then a variable number of parameters is what the ... means, okay? And it's important to know that on a stack-based CPU, you'll see an API, and then above it comes the parameters in reverse, okay? It's my one hint I'll give you in actually disassembling something. If you see a call like scanf, and it's going to do something, or printf, for example, printf takes one parameter. So right above it is going to be the parameter on the stack, okay? So in the assembler, and we'll cover this in a second, in the assembler, you're going to see printf and then the command, okay? Make sense? All right, we'll see that in a second. It's a little confusing. So let's take it apart. Put takes one parameter, char star, right? So load effective address, this, and just remember, load effective address is a pointer to something. So there's a key, right? The parameter is a pointer to something, right? So I have to load the effective address of this value. So that copies the memory space into EAX, okay? And then I move EAX into ESP as the stack pointer. Don't worry about that. This is just putting this on the stack, okay? Let's just say that. And then call puts, okay? So what's that telling me? I'm putting something out to the screen, right? I know exactly what this code is doing, and you really don't have to take this apart to know what's happening. If you read the API reference, you'll be like, oh, puts, it's right into the screen. And you can literally go through the program one line at a time and say, oh, I'm in this section. Oh, I'm in this section, okay? So something is written to the console. What about reading? So this is the code for reading, right? There's the scanf, and I know above it is going to be the parameters. So this is actually loading it into EAX. EAX onto the stack pointer, and it gets scanned in and it reads it there, okay? If I had more variables, if I read in 2 integers or expected 3 integers, then I would have seen more pushes onto the stack, okay? A lot of times you'll actually see the command push. This is just an optimization, so it's using moves with the stack pointer. It's GCC optimization stuff. Don't worry about it. So if we read something, what should be near it? What do we expect to happen? It's just read something off the console. What's it going to do? It's going to check it to something, right? It's going to say, hey, what's happening here? What did I just get? Was it good or bad? Was my input good or bad? 99.9% of the time. I'm not kidding you at all. I literally saved a guy's company with code that looked exactly like this. He hired a programmer. He paid him a lot of money to build him a piece of software. He didn't get the source code from him. He started selling the software. It had a licensing mechanism in it, okay? The programmer came back to him and said, I'll give it to you for 50% of your company. I will give you new licenses for the next year. So he called me up and asked, hey, can you look at this? I said, sure. It was in VB6. If you ever debug VB6, it's a nightmare. It's actually pre-obfuscated by accident. It calls so many VB-DLLs that stuff is everywhere. But it was funny. Once I got the program reversed, it actually turned out the guy was reading the serial numbers off the hard drive, reading some system IDs, blah, blah, blah. And at the end, it came down to one compare. One compare. He did all these checks, and at the end of it all, he just said, was it good or bad? And all he had to do was override that. And we'll talk about that. Because as soon as I changed it, I changed the what? If I change the memory, the computer's going to do what? Execute whatever the hell I told it to. Because it's all memory. I can change it all I want. That's the beauty of it all. So here, we're moving this pointer. This is off the stack, okay? It's something off the stack into EA. Then we're comparing it with 2A to EX. So this is comparing the value star with the value we just read off the console, okay? And this jump, what do you think J and E means? Jump not equal, exactly. What do you think JE means? JNZ. JZ. Awesome rapper. No, and then JMP. What's JMP going to be? All right, real simple, right? You can read this. It's right. It's like reading English. PowerPC opcodes are a little more annoying, but that's all right. So this is comparing the input to that, right? So what can we do about it? If I don't want to have this jump, what can I do? Or if I want to change the value in the inside, what can I do? Yeah, I can just edit it. I can go edit the program. Now there's way around that. How could I stop someone from editing my program? It's on their machine. I can't physically stop them from editing it unless I have trusted computing, which we don't have yet. So what can I do? Exactly. I can do another check, or I can do, everybody heard of a MD5 or a CRC32? I can run a stupid calculation over the memory range and say, as this is changed, it's going to have a different output value. If that doesn't mix, what happens? What can I do to that if I'm the reverse engineer and I want to get rid of that? I can get rid of that check. And what's it become? It's a cat and mouse race. That's all it is. It becomes a cat and mouse race. So the golden rule when you're writing a piece of software, in my opinion, for your security, 80-20 rule. Spend 80% of your time running the code, spend a little bit making a protection on it because someone wants to break it. What are they going to do? They're going to break it. I mean, I have friends who have reverse engineered the most massive software I've ever seen in my life. I actually know one guy who reverse engineered the Nintendo 64 dumps through a recompiler to actually native x86 code so it would run through OpenGL. He never released it, but it was amazing. I mean, it was ridiculous. This guy is one actually of the Microsoft developers. He was crazy cool. Amazing programmer. Assembly, he's the guy who can actually read that dump I showed you. I'm not even kidding. He's crazy. But it's cool. The other fun part is you can really impress your friends by listing off opcodes that you've worked with a lot, like E9. You know E9? Jump. Yeah, exactly. 9-0. Anybody know that one? NOP. No op. Yeah, we'll cover that one, actually. But once you do a lot of assembly, you're actually like, oh, that's what that is. Okay, cool. But we know it jumps when they aren't equal, okay? So it's not equal, right? J, N, E, jump, not equal. So we know that it's reading a value and checking to see if this is equal or not. If it's not, it's going to jump to another piece of code. That's exactly what that said, right? So we don't want that to happen. We want it to jump whatever I put in there, right? So if we can get rid of it, let's remove it, right? We can just get rid of it, okay? So no op for the win. One of your favorite commands if you're ever reverse engineering something and you just want code to go away. And in hex, it's 9-0. It literally just means no operation. The CPU is just like, all right, okay. Can I do something yet? No? Okay, cool. And it's funny because you'll actually see a lot of programs. Does anyone ever try to buffer overflow, like on your own machine? Anyone? You ever heard of a no-op sled? Anybody know what that means? So when you're overwriting memory, when you overwrite something, if you're not exactly sure where you're going to jump to in memory, you can do what's known as a no-op sled. You literally just put a bunch of 9 zeros, a bunch of hex. That's just 9-0, and it overwrites that memory space. And when the CPU, the EIP, the instruction pointer, jumps to that spot, it just starts sliding down the 9 zeros until it hits your executable code, okay? Does that make sense to everybody? It's a little strange, but that's how almost every buffer overflow works, all right? Hacking a machine is really easy. That's the funny part of it all. But so you find the hex for the opcodes, right? And it was in our dump. So we know this J and E. This is what we want to go away, right? This piece of code. And I know it's right here on this line, 7506. If I search in a hex editor for 7506, I can find it, and I can replace it with 9090, okay? And when it outputs that code, well, I didn't show it, but if you actually disassemble this again, instead of this J and E 0x01F1A, you're going to see no op on 2 lines, okay? So if I disassemble this new binary, you're going to see it changed. The program, the protocol has changed. The specification is different, and the CPU sees something different. So it's a new executable. And if I execute it, I can type anything I want, and it's just going to skip over that and exit the program. Okay, does that make sense? That is all there is to reverse engineering. That's it. You go in, you do what you want, you change the memory, you jump out. It's all right in front of you. So if you want to know more, you've got Google. You've got CrackMe's, which are a great way to practice this stuff and learn assembler. They're amazingly fun. Most people who do RE for a living or just have fun, this is a great pastime. Go to crackmes.de. Some amazing code people have written out there. Does anyone know Rolf Rolls? Anyone? He and I went to undergrad together. He's an amazing reverse engineer. He's actually the guy who did the first reverse engineering hack on virtual machine compilations. So in new protection in people's software is they'll launch, it's kind of like packing. They'll pack it, but they run a VM on top of it. And this virtual machine actually executes the code instead of ever converting it back out. So you never actually have the actual CPU binary. There's never the actual correct specification because it's got its own little CPU it's executing. And it makes it crazy. It's very hard to dump. But Rolf actually figured out a process to very quickly, once you know the opcodes, to dump and recompile the program, statically recompile it back to an x86 binary. So all this virtual machine crap becomes useless after like 20 minutes now. So it's pretty funny. These guys spend like 2 years building this crap, and it's useless. 80-20 rule. Seriously, just put a stupid little check. I mean, I don't even care if you have to type A. Like, it's something. Like, most people will be like, oh, that's cool, A, and not deal with it. Most people aren't going to mess with your code, right? They're never going to do with it. So if you need to protect code, it's the opposite. Just don't worry about it. Do a little bit, make it a little tough, and that's it. Everybody walks away. Reverse engineering in general, openrce.org. This is actually where Rolf posts all his stuff. You can actually find his papers on that. Rolf talks at all the reverse engineering conferences. He talks at DEF CON a couple times, blah, blah, blah. And IRC. Everybody use IRC here? All the cool people do. I guess somebody else is cool. I don't know. But no, IRC, there's some great reverse engineering channels, and they're really useful. I mean, some of them are dicks, the RTFM people. Anybody here an RTFM guy? We can go fight right now. I can't take that crap, man. It's ridiculous. Like, if I want to read the manual, I would have gone and read the manual. It's probably confusing. But so that's it. And I would like to point out, I used sweet clip art through here because the internet was out. And I just think it's pretty cool. Like, that's an awesome composition. Like, I should have been an artist. I'm just really proud of that. Just saying. So we can take questions. You just raise your hand. Jonathan Swift's Gulliver's Travels, the Indianness. Like, why is it that way, or like, what's the actual historical record of it? No, it's Jonathan Swift from Gulliver's Travels. He referenced the Indians. There was big and little.
That's how they ate an egg.
Yeah, down or the big end.
There's one political faction that puts the large end in the egg cup and cracks the small end, and then the other political faction puts the small end in the egg cup and cracks the top end.
So it comes from Jonathan Swift, like you said. Yeah, exactly. I haven't read that in years. Yeah, no problem. My pleasure. I did something useful. Woo! Hey, wait, where's Skydog? Somebody has to tell him I did something useful. Damn. Now he's going to beat me up. Anyway, I've got 2 minutes, a little more than that. Anybody else have any other questions? Did that make sense to anybody? Or did it just confuse the crap out of everyone? Okay, cool. Because I was just a little worried. Like, I know everybody wants to see a bunch of commands typed, but the truth is you got to know this stuff first. If you get this, you'll get it. Oh, yeah, if you check the bounds of what you're copying, you won't get a buffer overflow. Java's not, well, it is underneath, and we won't talk about that in the system stuff. But a Java array, for example, isn't susceptible to a buffer overflow because it checks the bounds of the memory it's going. So it says the buffer it holds, 128. And if it says the memory space I'm trying to read is 256, it just says no. It says index out of bounds, it throws an exception. And you can do it in C. You can just check. There's actually a copy that, there's a copy, a version of copy that has a comma, and then you just write the number that's the maximum to copy. And if you do that, you won't have a buffer overflow. Oh, yeah, hands down. No, it's a bad programming. I mean, you got to get her done. We got timelines. I mean, sometimes you might leave it in because you want to get back in later. Some people might do that. No. I'm an attorney. I'm not allowed to do anything. I don't program anymore. No, that's not true, actually. I program all the time. But, no, yeah, it's just sloppy programming. It's really what it is. And back in the day, it wasn't a problem, On the bulletin board systems, did anybody care? Like, oh, you rooted my machine. That's awesome. And now it's, you killed my machine. I just lost all my work for the last 2 weeks. I hate you. So that's the different worlds we live in. So anybody still in high school, it doesn't really matter if your machine dies, because that's when you learn the most. Because you're like, I'm going to go touch everything terrible. But then you grow up and you're like, oh, my thesis, you son of a. And other than that, there's actually different CPU architectures that prevent that kind of stuff. There's the von Neumann and there's the Harvard style, which I didn't cover here. These were all von Neumann examples. If you want to know more about it, please do. Wait, does anybody know how many memory levels an Intel CPU supports? So we've got ring 0. Everybody knows what that is. And then you've got user mode, right? How many other ones are there? There's 4. No, I told you that. But yeah, no, there's actually 4. So we've got ring 0, and then there's ring 1 and 2, which we don't use for some reason. Does anybody know an OS that uses them? Are they using all 3? I've heard that. As far as I know, there wasn't one.
I don't think there is anything, but there's like some government security level for OSs.
And if you have all, it moves up. I wouldn't doubt it.
The highest level of security is supposed to use them, but I don't think anything does.
No, I don't think anything does either. So it's just funny, Windows